Good morning, Sanghvi sahib. If I am audible.
Good morning, Patel sahib. Came show.
Happy to see you return in a battlefield.
કેમ છો સાહેબ મજામાં?
હા મજામાં.
Virat, we can start now.
Sir, shall we try? Shall we check with sharing?
Yes, please.
Shall we start, sir?
Yes, we can start.
Morning, participants. Today, on the final day of our SE, we will start this session with the our eminent personality, Professor Dr. C.S. Sanghvi, sir. The main point I would like to highlight is, sir is our backbone of this STTP as a coordinator, and he is a major motivator and inspiration for us to organize this training, and he has been a pillar of strength on our coordination. Now I will hand over to President Sirs as being the introduction and start our session for wonderful experience. Over to you.
Thank you, ma'am. Hello, namaste. A very pleasant morning to one and all present here. I, Rusit Chaudhary, on behalf of the Applied Mechanics Department, LD College of Engineering, Ahmedabad, and Government Engineering College, Modasa, welcome you all for the first session of the final day of this 5-day short-term training program on disaster management and resilience building, conducted under the aegis of Directorate of Technical Education in collaboration with Gujarat Institute of Disaster Management, Gandhinagar. It gives me immense pleasure to invite our next dignitary, Major Dr. C.S. Sanghvi, who is currently working as the head and professor of the Applied Mechanics Department, Government Engineering College, Modasa. Sir holds a bachelor's degree in civil engineering and master's degree in structural engineering from Gujarat University, and holds a PhD degree in earthquake engineering from SVNIT Surat. Sir has a professional experience of more than 30 years. Sir has presented more than 70 technical papers in national and international conferences and journals. Sir has also published various books on technical subjects. Sir has even guided 40 plus postgraduate and PhD students. We have a unique first in Gujarat Earthquake Engineering Laboratory at LD College of Engineering, which was established under leadership of Sanghvi sir. Sir has prepared 18 episodes on earthquake resistance construction for the civil engineering profession, which have been telecasted on DD national networks. Development project worth 1 crore of Earthquake Engineering Library for Government Colleges of Gujarat with GSDMA. Sir has conducted and coordinated training programs in the field of earthquake engineering for Class 1 and Class 2 officers of state government at Sardar Patel Institute of Public Administration, SPIPA. Sir has also coordinated various training programs along with IITs. Sir is actively associated with NCC and NSS activities in the states, and many students under his leadership are taking part in the Republic Day parade at Delhi and have received awards at the national level. And personally, I am very happy to say that Sir has received the National Award of the Best Program Officer of National Service Scheme NSS by former President of India, Sri Ramnath Kovind. Sir is the first officer with the rank of Major to become a centurion blood donor. Sir has organized many numbers of blood donation drive and thalassemia awareness drives. Even Sir has donated blood for more than 170 times. Sir is also the youngest centurion blood donor and has received the trophy of outstanding blood donor by the Indian Red Cross Society. Today we are going to be blessed with the knowledge and experience of Major Dr. C.S. Sanghvi sir on the concept of wake-up call, earthquake safe construction, challenges and way ahead. It is an honor of our department to welcome Major Dr. C.S. Sanghvi sir. Over to you, sir.
Thank you, Rushit and Deepa for the nice introduction. And today's session will start. I'm presenting my screen. Just wait for a moment. Can you see my screen?
Yes.
Is it visible, right?
Yes, sir, it's visible.
Yes.
Yeah. So, first of all, welcome all of you to this STTP on disaster management and resilience building, organized by Applied Mechanics departments of LD College and Government Engineering College, Modasa, in collaboration with the GIDM, Gujarat Institute of Disaster Management. Today's my topic is basically it's a wake-up call for earthquake safe construction. We'll talk about the challenges and how can we move forward to make society earthquake safe. So that will be the topic of today. And actually, we faced an earthquake in 2001, and almost 21 years gone by. And actually, what we have learned and whether we have missed certain opportunity to make our society earthquake safe. We'll discuss all these things in this lecture, and we try to understand what are the challenges we have as far as India is concerned. So I'm always starting my session with a basic slide that is regarding the disasters. We talk about the various disasters like earthquake, we talk about the cyclone, we talk about the flood, we talk about fire, we talk about the landslide, we talk about liquefaction, we talk about tsunami. If you look at all these disasters, then you find that all these disasters are very important from structure point of view. There are many more disasters, but these disasters are related with the structure. So I have included these disasters, and we may have some other disasters like chemical and biological. We have right now we are suffering from the pandemic corona. many other disasters, biological disasters we have, but we are not going to discuss those because we are going to discuss the disasters which are very important from structural point of view. And when these disasters comes in picture, generally we are classifying these disasters into the two category, either they are natural or man-made, right? So most of the time we are saying the earthquake is a natural disaster, cyclone is a natural disaster. When we are talking about the flood is natural or man-made? Most of the time the flood is natural, but sometimes it is man-made also. For example, if you consider the case of Machu Dam collapse in Morbi in 1979. So the main reason of the collapse of the Machu Dam was uh, that there was a excessive rainfall and the water overtopples, and during that time they are not able to open the gates, and this uh, 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 the reason of not opening the gate was a poor maintenance, and this is the human error, so you can say it's a man-made disaster. So sometimes because of the wrong decision the area is flooded. That is also the case of man-made disaster. So flood may be considered as a man-made disaster or the natural disaster. Same with the comes and we classify into natural or man-made. Same with the landslide also. The landslide most of the times it triggers because of the earthquake. It's a natural, but sometimes for the mining we are exploding or we are going for the explosion in the hilly region, and landslide triggers, that is man-made. The liquefaction, the liquefaction again, uh, if we are not able to assess the geotechnical features of the soil, then this liquefaction problem may occur. If you are knowing that my building is founded on sandy soil and water table is high, in that case there are possibility uh, of liquefaction. And if we are not able to identify this risk, then we can also say it's a man-made disaster. Because when you construct any structure, you must have a geotechnical profile, and if you don't have the geotechnical profile and you are constructing, and if it is a cohesion layer soil and water table is high, then the definitely the during the earthquake liquefaction is possible. So uh, uh, we don't have a good geotechnical investigation, and therefore liquefaction occurs. So therefore it is man-made. uh, the tsunami most of the time is natural. The, it cannot be man-made. Now you see, when we are saying it's a natural disaster, natural disaster means nature is very angry, and during the natural disaster generally we are not approaching nature. For example, a cyclone. Suppose we are uh, in our house, and suddenly cyclone hit, uh, and what we do, definitely we feel safe within our house, right? Definitely we'll feel very safe in our house, and we are not going outside in case of cyclone, right? But suppose um, if earthquake triggers, and we are on the ground floor, so what will do uh, what do you do in that case? Definitely we try to go outside, we try to go to open space, isn't it? And this open space is nothing but it's a nature. So in cyclone, you are not going outside, but in case of earthquake, you are going outside in open space. So some contradiction is there. So when we are saying cyclone is a natural disaster, earthquake is a natural disaster, but uh, during cyclone, you are not approaching nature, and during earthquake, you are approaching nature. You are going to open space, right? So the question will arise: why we are running out of our building? Why we are running out of uh, uh, our house? What is the reason behind it? Because we feel that During earthquake, if building will collapse, then we will die, and that fear we have in our mind, and therefore we are running out of the building. And who built this building? Basically, we civil engineers have built this building, and therefore uh, we are always saying that earthquake do not kill, earthquake do not kill, but the unsafe buildings do. Right? This is very important. Right? Remember this thing. Uh, Suppose there are no buildings and you are actually in open space and a earthquake triggers, nothing is going to happen. But the disaster which is taken place, that is because of unsafe building, collapse of the unsafe building, right? So therefore we are saying that the earthquake do not kill, but the unsafe buildings do. If all the buildings are safe, there is no need to run out of the houses. So therefore we are always saying that earthquake is a natural hazard, but the disaster is man-made. Remember, earthquake is a natural hazard, but uh, it is a man-made disaster. And therefore the most important thing is this, that the solution lies in the building. Remember, solution lies in the building, not in the earthquake. So as a civil engineer, we have to focus on the building. We have to construct the safe buildings, safe structures, right? It is the need of the hour. And if you look at this picture, and you will find that with every disaster, the two things are associated. One is a fatalities, and another is the economic loss. These two things are always associated with the disaster. And if we consider the fatalities, loss of life, if the 100% or if you say 100 people die in disaster, out of this 100, 47 die in earthquake. Remember, 47 out of 100, 47 die in earthquake, 45 die in cyclone, 7 in flood, and 1 in other disaster. And if you look at the economic loss, then the contribution of earthquake is the highest, 35%, right? So the highest economic loss among all the disaster is coming from earthquake. 28% from the cyclone and 30% from the flood, and the remaining disaster 7%, right? So this is very important to understand, right? The maximum contribution in case of loss of life is coming from earthquake, and economic loss is also coming from the earthquake disaster only, right? So therefore earthquake uh, uh, engineering is very important for us, and earthquake resistant design is very important for us. And in this case, if you look at the case of the flood, in case of the flood, if you look at the loss of life is very less, but the economic loss is very high. What is the reason behind it? The main reason behind it is that we are able to predict flood right now. And as we are able to predict flood properly, so people are going to the safe places, and people are evacuated from the dangerous condition, and we can save loss of life. But their property and other valuable things are drawn off, and therefore the economic loss is very high. In case of earthquake, we are not able to predict earthquake right now. People are working on it. People try to predict earthquake, but right now we are not able to predict earthquake. If we are able to predict earthquake, then loss of life can be reduced. Nowadays, we are able to predict cyclone very much. So the loss of life in the cyclone is reduced. And same way, in the future, if we are able to predict earthquake, then we can reduce loss of life during the earthquake disaster. So this is very important. But right now, we are not able to predict earthquake, and therefore loss of life is very high. At the same time, you see economic loss is always be associated, and yeah, for by making the better approach in the designing, we can reduce the economic loss also. The challenge, we are talking about the challenges. The first challenge we have is the earthquake. It's a primary disaster, but there are many other disasters which are there because of the earthquake, and we are knowing that the tsunami is a result of the earthquake. Maybe tsunami is not that frequent. If there are uh, uh, 100 big earthquakes, you may observe a tsunami, right? So it is not frequent that for each and every earthquake you will see the tsunami. No, but tsunami is a earthquake is a rare phenomena, and again among all the earthquakes, tsunami is also a rare phenomenon. Right. Liquefaction is observed in case of a cohesion-less soil. Uh, the fire, sometimes the fire is uh, there because of the earthquake. Uh, the, the, the the biggest example was the 1923 Tokyo earthquake. 1 lakh people burned alive. In the Tokyo city, uh, the 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 gas pipelines were there, and this gas pipeline were disturbed, where disturbed and gas leakage was observed, and almost the half of the Tokyo city was under fire, and 1 lakh people burned alive. So the fire may be broken out because of the earthquake also. Landslide is the another problem. The flood, sometimes because of the collapse of the dam, or the small dams, maybe area is flooded. This is the possibility, and the nuclear disaster. Right. So in 2011, we have seen a Japan earthquake. Right. Means this Japan earthquake was known as a triple disaster, because Japan has observed earthquake of magnitude 9, right? And this earthquake was followed by the tsunami and a nuclear disaster. So Japan has observed 3 disasters at a time. One is earthquake, then tsunami, and the nuclear disaster. So this is the worst thing. And I tell you, if you look at the position of the Bombay, then the Bombay is in zone 3, Mumbai is in zone 3. So there is a possibility of the big earthquake, and it is near the coastal region, so possibly tsunami is also there, and we have the atomic research center, so nuclear disaster is also possible. So we have to think from this perspective that what are the possibility of these disasters in India also, right? So the main challenge is the earthquake, but we have the secondary disasters because of earthquake. That is considered to be the challenge also. If you look at the global occurrence of the earthquake, right? Most of the time, the earthquakes are classified on the basis of magnitude, right? If the magnitude is 8 and higher, we are saying it's a great earthquake. And how many earthquakes we are expecting? We are expecting 1 great earthquake per year, right? So on the right hand column, it is given annual average number, right? This is what we are expecting in a year. So we are expecting 1 great earthquake. If you are talking about the earthquake of magnitude 7 to 7.9, we are expecting 18 earthquakes. Strong earthquake of 6 to 6.9 magnitude, we are expecting 120 earthquakes. Now, if you look at this, you find that if the magnitude of the earthquake decreases, what is happening? This number increases. Number of earthquakes increases. If I'm talking about the earthquake whose magnitude is less than 3, then you'll be amazed that there are 9,000 earthquakes, 8,000 and 1,000, right? Total 9,000 earthquakes are daily taking place, right? 9,000 earthquakes are regularly taking place, but we are not worried about these 9,000 earthquakes. The reason is the amount of energy released during these earthquakes are very less, and they are not putting any threat to our buildings. This is the main reason, right? So uh, our earthquake resistant design philosophy is hiding behind this. So remember, this this table is very important for us, and we have to conclude something out of this. And what can we conclude? We can conclude that the big earthquakes are rare. The big earthquakes are rare. Moderate earthquakes are occasional, and the small earthquakes are frequent. Remember, this is the conclusion of our previous slide. This is the conclusion of this slide, right? So this is the conclusion. Very simple example I'm taking. I'm comparing two structures, right? I'm comparing two structures. The first structure is these structures are located in the Kutch region, right? Remember, this is located in the Kutch region. The first building is constructed in 1818, and another building is constructed in 1820, right? Now we are knowing that in the Kutch we have a great earthquake. We have a great earthquake in 1819, and then we have a next major earthquake in 1956, right? So after how many years? Almost 137 years, right? 137 years. Remember. So this is very important. Now, what I'm saying, I'm comparing these two structures. I am assuming the life of the structure is 100 years. Remember, life of the structure is 100 years, right? Right now, for that, you'll be amazed that in Gujarat, the tall structures are permitted right now, right? So now you will see tall structures in Gujarat. Tall structure means a structure whose height is more than 100 meters. So permission is already started, and these tall structures are designed for 50 years. Remember, these tall structures are designed for 50 years right now. So as per the codal provision, designed for 50 years on. I am assuming 100 years right now, right? So my first building was constructed in 1818, and his life will be over by 1918, right? So this is the 100 year, right? So uh, uh, we have an earthquake in 1819. Remember, we have an earthquake in 1819. So this building has observed a great earthquake, right? This building has observed a great earthquake, and uh, if we want to learn something from experience of this building, then what we can learn, we learn that we have to design our building as earthquake proof. Earthquake proof means we have to design for no damage condition. No damage condition means our structure is safe, and our structure is safe, but at the same time, when we are designing for the no damage condition, it will become uneconomical. It will become uneconomical, right? Now we take the second structure. The second structure is constructed in 1820, right? And if I'm designing for 100 years, then the life of this will over by 1920, right? Now we have a great earthquake in 1819, right? And then we have a next earthquake in 1956. So how many earthquakes this building had observed? So this building has observed not a single earthquake during the. This building has not seen a single earthquake, single major earthquake. I'm saying single major earthquake during the life, right? So these are the two contradictions. This building, which is constructed in 1818, has observed a great earthquake immediately after its construction, and the another building, which is constructed after 2 years, had not seen any earthquake during the life. So if we learn something from the experience of the second building, then second building is saying that there is no need to design building for earthquake, right? But we are knowing that the earthquake is not a sure event. Earthquake may occur at any moment. This building is lucky that this building has not seen any earthquake, but the earthquake may come at any moment, right? And if earthquake will come, then definitely if you are not designing your structure for earthquake, it will collapse, right? So it is unsafe. So you cannot make your structure unsafe. So you have to design your structure, right, for earthquake. So the problem with the earthquake proof design is that it is safe, but it is uneconomical. And if you don't design, it will become unsafe. So this option is not there at all. So we are going for the another option. What is the another option? The another option is we are saying that, okay, uh, uh, remember this force. This is the actual. This is a maximum force, right? This is the maximum force which is coming on your structure because of the earthquake, right? And actually, you suppose, for example, this load is 100. For example, this load is 100, right? The load coming is 100, but we are not designing for 100, right? Right. So what we do here, we are designing for only this much force, right? This much force. It is almost 20% of the actual force, 20%, 30%. So basically, what we are doing, we are not designing our structures for the maximum force. We are going for the some alternate approach, which is known as the earthquake resistant design. In earthquake resistant design, we are trying to make our structure ductile. We try to design our structure in such a way that it will absorb the energy which is supplied by the earthquake, right? That is the main thing. So we try to design our structure for the ductility. We rely on the redundancy, we rely on the overstrength, right? So basically, what is happening during the earthquake? During the earthquake, energy will release. Lot of energy will release. Now this energy will travel in form of waves. Now these waves will shake the foundation of the structure, and some of the energy is entering into our structure, and we have to make our structure such that it will able to absorb this energy. So we are knowing that the brittle material cannot absorb more energy, but the ductile material absorb more energy, right? And therefore we try to make our structure ductile, right? And we try to absorb the energy which is supplied by the earthquake, right? So that is so here our philosophy of earthquake resistant structure is that we assume that earthquake is not a sure event, and therefore we are taking the chance, and what we do, we go for the earthquake resistant design. What is earthquake resistant design? The damage is allowed, but collapse is not allowed, right? Remember, collapse is not allowed. Collapse is not allowed means it is safe, right? And remember, here you are not designing for 100% force. You are designing for only 20%, 30% force. When you are designing a structure for or structural element for 20% or 30% load, then definitely the sizes of the structural member will come down, and your structure will become economical, right? It will become economical, right? So this is the only philosophy in which damage is expected. Remember, damage is expected. This is the only philosophy. When we design our structure for dead load and live load, how we design for the dead load and live load? We apply factor of safety 1.5, right? So if the load coming on your column is 100, you are designing for 150 kilonewton. So we are not expecting any damage in case of dead load and live load. But in case of the earthquake, we are expecting damage. What is the reason why we are expecting damage? Because our structure may enter into this inelastic zone. Remember, our structure may enter into this inelastic zone, and when it enter into the non-linear response, always some residual deformation will be there, and this deformation will result into the damage, right? So these are the permanent deformation which is taken place. So we are allowing permanent deformation in our structure during the major earthquakes, right? So remember, understanding this philosophy is also a challenge, right? Understanding this philosophy. During the 2001 earthquake, people, when we visited the various buildings which were damaged, and when we went there, the people are saying that how can you allow the damage in the structure? So you see, earthquake is a rare event, and as earthquake is a rare event, we are taking chances. We are taking chances not in case we are not making our structure unsafe. Remember, we are taking chances. Which chances we are taking? We are saying that if my building, like this building, if my building will not see any earthquake, then I am saving lot of money, right? But if my structure will see earthquake, then it will observe damage, right? And as we are not sure that my building will see earthquake during the life, if it is sure that my building will see 5 earthquake or 10 earthquakes during the life, definitely I will go for the earthquake proof design. But I'm not sure whether my building will see a single earthquake during the life. Therefore, I'm going for earthquake resistant design. And earthquake resistant design is a safe design. Remember, damage is allowed, but collapse is not allowed under any circumstances. Collapse is not allowed. And therefore, it is a safe and it's so economical, because we are not designing our structure for 100% force. We designing for the 20% force. But we design our structure in such a way that our structure is able to take, or our structure is able to absorb the energy which is supplied by the earthquake, right? So we are designing our structure as a ductile structure, right? And as we are designing as a ductile structure, we are expecting damage. And what is the risk? Risk is that if earthquake will come, our structure will absorb damage, and we have to retrofit our structure. It is also possible that damage is taken place to that extent that we have to demolish our structure after earthquake. It is also possible. But remember, collapse is not allowed. Damage is allowed, but collapse is not allowed, right? So this is the philosophy. The philosophy under the minor shaking, that the damage to the non-structural member is allowed. In case of a moderate shaking, heavy damage to non-structural member, this is the, I'm talking about RCC structure, and some damage to the structural member also. And in case of a strong shaking like Bhuj earthquake, we observe a heavy damage to the structural member and the non-structural member. But the bottom line is, our structure is not going to collapse. This is the bottom line. No collapse is allowed at all. So we have to digest this philosophy, right? As a civil engineer, as a structural engineer, and during the earthquake, we have to understand that damage is allowed. Your building has to survive during the earthquake. Building should not collapse during the earthquake, right? That is the. So this is the philosophy in which under minor shaking, we are allowing repairable damage in the non-structural member and no damage to structural. Under moderate and occasional shaking, there is a heavy damage, because you see, we have earlier concluded that big earthquakes are rare, moderate earthquakes are occasional, and the strong earthquakes and the small earthquakes are frequent, right? So here, this is the moderate earthquake, which are occasional, so heavy damage to the non-structural member and repairable damage to the structural. And under the strong but the rare shaking, very heavy damage which is not repairable to non-structural member, and so very heavy damage to the even structural member. But the thing is, no collapse, right? This is required. So again, I'm saying this philosophy is very important for us. I'm always saying earthquake is a warlike situation. Warlike situation means in war, we are sacrificing people from the armed forces to save the nation, right? Remember, this is very important. Earthquake is a warlike situation. Again, I'm repeating. War, during the war, what we are doing? We are sacrificing people from the armed forces to save the nation. And in earthquake, we are sacrificing our structural members to protect the structure, right? Remember this thing. So this is very important for us, that the damages are allowed in this member, right? Is allowed, and the sequence is also important for us. So just I'm summarizing. We are not going for earthquake proof design. But what is earthquake proof design? We are designed for the maximum expected force, and we assume that our structure will remain elastic. So no damage condition we are expecting. So it is safe, but it is uneconomical. In this case, ductility is not required. But in earthquake resistant design, we design for certain level of expected force. What I said, we go for the, we have a, suppose 100 kN force is coming, we're designing for 20-30%. But on which we rely? We rely on inelastic deformation. Inelastic deformation. So we design our structure in such a way that it undergo large inelastic deformation, and that is possible because of the ductility, right? And because of that, the damage is expected. So this design is safe and also the economical. But the only problem with the design is be ready for the retrofitting in case of a major earthquake, right? This is the limitation of this philosophy, right? Now, our philosophy is saying that the building should not collapse, but the buildings are still collapsing during the earthquake, right? Buildings are still collapsing during the earthquake. If you look at the 1994 Northridge earthquake in America, we have seen the collapse of the structure. 1995 Kobe earthquake is known for the collapse of the bridge structures. 1999 Turkey earthquake, it is also known for the damages to the commercial and residential buildings. And we know the 2001 Bhuj earthquake. We have observed the tremendous devastation not only in the rural region but also in the urban region like Gandhidham, like Ahmedabad, right? So this was the one of the major earthquake which hit the urban region, and it had created a lot of questions to the preparedness, right? So the Handy Taken call, a structural engineer who is from the California, he said that this is a very important statement. Some of us just read this statement. This is very important. Some of us used to argue that you shouldn't really get your structural license until you have chased an earthquake. आपको तभी आपका स्ट्रक्चरल लाइसेंस मिलना चाहिए जब आपने एक earthquake देखा हो. What is the reason? The reason is no matter how much you read the report, the impact doesn't really strike you until you have seen the damage and casualty. जब तक आपने डैमेज नहीं देखा है, जब तक आपने कैजुअलिटी नहीं देखा है, तब तक आप कितना भी रिपोर्ट में क्यों ना पढ़ लो, लेकिन वो जो इम्पैक्ट आपने जो देखा है वो कहीं से नहीं आएगा. So if you have seen one earthquake, then definitely you will go for the honest practice because you have seen lot of damage and casualty, right? And in my opinion, we have seen the earthquake of 2001, and after that, I think we have seen the tremendous change in the practice also, right? We still, after 21 years, I'm not able to forget that earthquake. Remember, during this earthquake, our NCC cadet has supported the Indian Armed Forces. Indian Armed Forces were deployed in the Ahmedabad city, and they have cordoned the site which were collapsed, and basically they are bringing the dead bodies and the valuables from the collapse site, and our NCC cadet were supporting the Indian Armed Forces in this work. And almost we have worked for almost 4 to 6 months during this time, and almost my NCC cadet brought almost 24 dead bodies from the collapse site, and I was also there, and I brought a dead body of 4-year-old boy from the collapse site. And you see, still I'm not able to forget that particular thing. Still I remember that picture in my mind. And you see, if you have seen this, definitely you are not able to forget this thing, right? So this is a very important statement made by the Henry Degenkolb. This is the very emotional statement he made, but this is the fact that if you have seen an earthquake, definitely you will do your honest practice. If you look at the, you see, we see such type of pictures during the earthquake. This type of picture definitely will distract you as a civil engineer, right? we are not expecting such pictures. This is the picture from 2001 earthquake, right? So remember, we do not expect such things during the earthquake. After the earthquake, this should not happen, right? So this will definitely distract you. Now, what is the challenge? The challenge is the mode of denial. We have a attitude, right? The attitude of what? Mode of denial, right? When the earthquake taken place, we have seen a tremendous collapse in the Ahmedabad and Gandhidham city, and at that moment, the uh, the builders are saying that the earthquake which taken place in 2001 uh, was uh, actually the unusual shaking. It was above our expectation. This was the argument raised by the builder in the court. That, again, I'm saying, the shaking or the acceleration what we felt at Ahmedabad, it is beyond the expectation, beyond the intensity which is expected by the code. But during that time, in the passport office, we have a accelerometer, and uh, we have find out the intensity there, and you'll be amazed that Ahmedabad is in zone 3, seismic zone 3. So the expected intensity was 7, and the passport office, the seismometer is saying that the intensity was 7 only, right? So it means it is not unexpected shaking. It is not the shaking is not beyond our expectation. The Bhuj is in zone 5, so the intensity expected is more than 9, and the intensity was 10. So it is as per our expectation. So the 2001 earthquake is not a case of unusual strong shaking, right? But why this disaster was taken place? It is because of the unusually weak buildings in the city. Remember, it is because of the unusually weak buildings in the city, right? In the Bhuj earthquake, of 2001, magnitude was 7.7, 13,805 died, right? If you look at the Ahmedabad is located 300 kilometers from the epicenter, and in Ahmedabad, 130 multi-story building collapsed. 130 multi-story building collapsed in Ahmedabad. 752% killed, right? So out of these 130 buildings, 2 were ground plus 10 story, and rest of them are ground plus 4 story building, right? Ground plus 4 story building. Now, most of these buildings are new. Almost the life is 10 years. अभी तो उनका सिर्फ 10 साल ही हुए थे, and most of them are designed by the architect and the engineers, built by the developers. Most of them, I'm saying most of them, right? And this building were collapsed. It means we have committed certain mistakes. We have to accept that, right? And if you look at the old Ahmedabad means हमारा जो पुराना Ahmedabad है, जहाँ पे पुराने buildings है, no collapse of a very old buildings in Ahmedabad, right? So what are the reasons? The reasons of collapse are the total disregard to the structural system. Remember, structural system. At that time, generally you say we are constructing the lift well of RCC, right? Generally we are constructing with the RCC, the lift case, right? So during that time, the people are constructing not by the RCC, they are constructing with the masonry also. Just understand this thing, right? They don't understand the effect of shear wall. This lift valve will behave like a shear wall, and it helps a lot during the earthquake. People are not understanding. Even structural engineers are not understanding. So structural systems we have not gone for the good structural system, uh, structural design principles, quality of construction, and construction practice, right? So these all points are not uh, considered. They are total disregard to this points had been observed. Right? The many buildings are unsafe even to carry gravity loads. Right? This is the fact, I tell you. Sometimes we also hear the news that the building collapsed without the earthquake. Right? Yeah. So this is happening. This should not happen. Right? So the total loss was almost 25,000 crore at that time, and just imagine if the similar earthquake is taken place on the northeast boundary, then it will become more expensive, I tell you. Right now, uh, generally we have to learn from the past earthquake, right? Learn from the past. Now 2001 Bhuj earthquake, the intensity was 7.7, 13,805 people died. Right, the intensity was highest is 10 on modified Mercalli scale. Now question will arise, was Bhuj earthquake a first earthquake in India to hit the urban region? वो भूज earthquake वो पहला earthquake था जो urban region में hit किया? The answer is no. Answer is no. We have seen 1997 Jabalpur earthquake. 1997 Jabalpur earthquake. Now Jabalpur is a city like Ahmedabad, and this Jabalpur was hit by the earthquake of 6 magnitude, right? And during that the urban area is affected, but no lesson is learned from this earthquake. No lesson is learned. Why? The reason is the number of death from this earthquake is only 38. सिर्फ 38 लोग मरे थे इसमें, एंड हमारा जैसे कंट्री जैसे इंडिया में 125 करोड़ का देश हो, उसमें से 38 लोग मर जाए तो उससे क्या फर्क पड़ेगा? सो वी हैवंट लर्न एनीथिंग फ्रॉम दिस अर्थक्वेक. ये 38 लोग तो दारू पीने से मर जाते हैं, isn't it? तो ये 38 लोग मरने से we haven't learned anything from this earthquake. If we have learned something from this earthquake, तो हमने अहमदाबाद में जो हुआ उसको हम रोक सकते थे, right? But we haven't done this, and we have seen a tremendous devastation in 2001 Bhuj earthquake, right? So learning from the past earthquake, we are not learning properly from the past earthquake, right? The construction practice is also a challenge, right? As the buildings are still collapsing during the earthquake, it means someone from the construction industry is or are responsible for this disaster, right? Who are the stakeholders of construction industries? कौन है construction industry के stakeholders? First is a builder or owner, right? Builder and owner, he must be honest, right? His aim should not be earn money only, but he has to provide safe habitat. That is the requirement, right? So this builder or owner has to appoint a good architect, and this architect must give a good configuration, good planning. We are knowing that the unsymmetrical structures produce the torsion during the earthquake, and your structure is going to perform very poor during the earthquake. So the architect has to give good configuration, a symmetrical structure he has to give. So half of the problem will solve in that case. And the structure engineer appointed by the owner must be good enough. So he is going to provide the safety to the structure, right? So a good structure engineering practice is required, and structure engineer is the most important person to construct earthquake resistant houses, because you see here the margin of error is very less. If you commit certain mistake, your safe house will become unsafe, right? And the structure engineer is the key person. The site engineer is also important, because the planning which is given by the architect, the structural design given by the structural engineer. The site engineer has to execute this on site. So he has to execute as per the instruction given by the structural engineer and the architect, and he has to maintain the quality of construction on site. So site engineer is again a very important person. Then we have a mason and bar bender. We are knowing that the mason is equally important and the bar bender, because we have to go for the ductile detailing as per 13920. So the quality of bar bending is also required, and masonry work is also required. The authority means the urban development authority or municipal corporations. They have to enforce the codes, bylaws, GDCRs. They have to implement in a very strict way, right? Strict implementation of this building bylaws, codal provisions, and GDCR is required, right? And if authority decides that we want a safe houses, nobody can do anything, right? Uh, uh, I'm giving you example of New Zealand. In the New Zealand, the Christchurch. In the Christchurch, they are uh, going for the assessment of each and every building, and then after assessment, the assessment is done by the qualified structural engineer, and at the end of the assessment, each and every building is tagged with earthquake safe or earthquake prone tag, right? If your structure is earthquake safe, it is okay. But if your structure is tagged with the earthquake prone, then earthquake prone label, then you are in trouble, because you have to improve your structure. The Christchurch authority, municipal authority, will give you a warning, and they give you some time that you have to improve your building within 5 years. And if you're not able to improve your building within 5 years, then government will take charge, right? So punitive actions, the punishments are there, right? So such kind of model should be applied in India. Then and then people will go for the serious practice as far as construction industry is concerned. And teachers and students, like teachers are teaching in the colleges the subject, and the students are learning, and then these students become professional engineers in future. So this is the way a capacity building process is taken place. So uh, these all are the stakeholders, and these are the attribute we need from each and every stakeholders to make the society earthquake safe. The another challenge is the errors we are committing in the safe construction. There are three types of errors we are committing: error of intention, error of concept, and error of execution. These three types of error generally we are committing. Error of intention means I'm knowing everything, but I do not want to do it, right? So this is basically negligence, and it is not allowed at all, right? The error of concept means uh, I'm not knowing the correct earthquake resistant design, and therefore I'm committing certain mistakes. That is the error of concept. An error of execution means it is properly designed, but it is not executed. The structural design given by the structural engineer is not executed properly on site, right? So out of these three, the error of intention is the worst, right? Error of intention is the worst. So uh, 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 you have to be very honest in that case. But most of the time, as far as the construction industry is concerned, we are committing error of concept and error of execution all the time, right? So error of concept we have seen during the 2001 earthquake. Error of execution is also we have seen during the 2001 earthquake, right? So these are the common errors we are committing on site and on practice. The another challenge is the structural engineering challenge, right? We are designing our structures. We are designing our structures for the loads which are acting on it, right? And there are different types of load acting on the structure. These loads which are acting in the direction of gravity, they are dead load and the live load, right? Now, these loads, dead load and live load, they are permanent in nature, because the dead load is the load self-weight, and the live load means we talk about the human load of furniture and other loads, right? So it is supposed to come on your structure. So we treat it as a permanent load, and I talked earlier that suppose a load of 100 kilonewton is there coming on your column, so you multiply by 1.5 factor of safety you are using 1.5, right? And basically you are designing for how much force? 150. Instead of 100, you design for 150, right? So if you design for 150, means you are not designing for any damage. Your structure is not going to damage. So you are designing your structure for no damage condition. Remember, this is very important. When you design your structure for dead load and live load, you are designing for no damage condition, right? But when it comes to the lateral load, wind and earthquake, we are knowing the wind force is quite frequent as compared to the earthquake. If your building is located on the coastal region, your building may observe 3, 4, 5 cyclones during the life. It's possible in 100 years or 10 cyclones. It's possible. But in case of the earthquake, we are not sure whether our building will see earthquake or not, right? And this earthquake is only acting for maybe effective time is only of 2 minutes, right? So this earthquake may act on your building or may not. First of all, there is a probability. So earthquake may come during the life, may not come during the life, and if it will come, maximum effective time is almost 2 minutes in most of the earthquake we have seen, right? So this is the condition we have, and we design for this our structures for this 2 minute force, right? So we design our structure for damage condition for no collapse, right? This is the philosophy we have understood earlier. So what are the deficiencies observed during the earthquake, right? The deficiency what we observed is, the first is, generally we are providing the space for the car park or the vehicle parking at the ground story, right? So when we go for the vehicle parking at the ground story, we are not constructing any wall, only column are present. Look at this, the column is there, here column is there, right? Column is there. So on the ground story you have only columns, and on the first story you have column plus wall, both the things you can see here, right? Both the things. So this type of structure is known as open ground story structure. Open ground story. Now here you can see this wall is constructed after earthquake. This wall is constructed after earthquake, right? They understand the importance of this wall later on. But generally we are not constructing wall on the ground story, and we keep ground story for the parking. You can see this, right? This is this is the open ground story. Open ground story, right? Now, what happens in case of open ground story? We are knowing that on the upper story you have column plus wall. So the upper part is very stiff, and the lower part is very flexible because there is no wall. So when the lateral load, when the earthquake load comes, in that case, the most of the deformation is concentrated at the ground story, right? So what is happening on the ground story? The deformations are concentrated on the ground story, and we are knowing that the column is having limited deformability. Suppose the total deformation is 100 mm at the top. Now this 100 mm is supposed to be distributed along the height, but in this case, the out of 100 mm, almost 70-80 mm is actually at the ground story, and therefore the ground story column fails. And we have seen this type of devastation during the past earthquake. Just look at this. Here, a ground story columns are collapsed. right? And the upper story are almost safe. Nothing has happened to upper story. So this is the open ground story failure. Look at this. This is the ground story columns. Ground story columns are collapsed, and the upper part is remained intact, right? उस टाइम वो बोल रहे थे कि मेरा पूरा पूरा मकान एक फ्लोर जमीन के अंदर चला गया. ये जमीन के अंदर नहीं चला गया. ये ग्राउंड फ्लोर कॉलम कोलैप्स हो गए and the whole building came down by one floor. Right. Now this is the classical photograph. You can see here the good mountain range here, right? So definitely as an owner, what I prefer, I want a good view of this natural nature, right? So what I did, I have provided the glass panel at the ground story, right? And by doing that, I'm making my structure soft, open ground story, right? Because the stiffness of the glass is very less, and therefore it absorb the damage because of the open ground story, right? This is the example of 1971 San Fernando earthquake. This is again a 2001 Bhuj earthquake. This ground story columns are collapsed, and we have seen this devastation, right? Open ground story. I tell you, in 2001, the multi-story buildings which are collapsed, out of that, the 130 buildings in Ahmedabad, almost 95% building collapsed because of the open ground story. Remember, right? This is another example where the ground story columns are collapsed. And here, the additional torsion came in picture. Remember, the whole building undergo, because this structure is unsymmetrical, and therefore the damage and the collapse is also of different type. So what can we do? What can we do? The very simple thing that on the ground story, columns were not, walls were not there. We construct the wall here on the ground story, but when we construct the wall on the ground story, we are sacrificing parking. Remember, we are sacrificing parking. So we need parking, and therefore this option is not okay. So what can we do? We can go for the shear walls, because the main difference is on the upper story we have walls, and the ground story we have only columns. So on the upper story we have column plus wall. On the ground story we have only columns. So we have to increase the stiffness of the ground story, right? And we have to avoid the soft story. So shear wall we have to introduce in a such a way that parking is also possible, and at the same time we are able to increase the stiffness of the ground story. Another option, this is generally we are executing in case of a steel structure. Instead of shear wall, we are going for the bracing. Right? So in case of steel structure, the bracing, the purpose of bracing is also the same. It will increase the stiffness, and the difference between the stiffness of first story and the ground story is eliminated, right? And the another option we have is we can design the ground story column for the higher earthquake force 2.5 times. Then the sizes of the column will become bigger, and the size will become bigger. Then the stiffness difference between the ground story and the first story will become negligible, and the open ground story is avoided like that. The another problem is a short column effect. Right? Sometimes we don't understand whether the short column is good or the long column is good, right? So we have to understand that short column, how the short column is suppose your building is located on a slopy ground. So in that case, this is a long column and this is the short column, right? So this may happen, or sometimes on the ground story we have a height which is more than the upper story. Suppose The upper story height is 10 feet. Above the ground story, we have a 16 feet. So what we do, we provide a mezzanine floor here. When we go to the mezzanine floor, the column becomes short. This column become this column, and this column becomes short. Right. Then what happens? Whether the short column is good or bad, that is the question, right? So simply our answer is that suppose this is the column, right? If this is the column and the load coming on the column in this direction, this is the axial load. The another column is a long column, right? This is the, suppose a long column, axial load is coming on this. So definitely the short column performs better in case of axial force, and this long column may buckle, right? Buckling may take place or bending will take place of this long column, right? So for the gravity load, the short column looks good, but for earthquake, when the lateral load will come, when the lateral load, earthquake force is also vertical direction and horizontal direction also. So if a horizontal load due to earthquake is coming, then what is happening? Short column is good or bad? Now we have to decide. You can see this. This is the case in which you can see these are the columns, right? These are the columns, and what the owner has done at the end. This is the ground story. So compound wall was constructed, and some gap was kept here, right, for the ventilation. So what happened in that case? This column is surrounded by these two walls. So this column becomes short. And what is the height of the column? Actually, the height of the column is only this much. Actually, we have designed our column for this full height, right? This height is L, and now the height of the column will become maybe L by 3, for example, right? This column height will become L by 3, and the column becomes short. Instead of height L, it become L by 3, right? And you can see the damage. Why this damage is taken place? What is the reason? We'll look at that part, right? This is the another example which was exposed in 1994 California earthquake. This is a multi-story car parking, right? Now here, this column is designed for the full height, right? This column is designed for the full height, and then this height is L, and after that, this parapet wall is constructed. So now the height of the column become only L by 2. Remember, L by 2, half. Right? The parapet is required for the safety of the car, and so they constructed. Nothing wrong, right? But by doing that, column become short, and earthquake is identified, and you can see the damage. This is a which type of damage you have. It's an X type of cracking, right? Again, you can see here. This is the another example, right? Here there is a wall. Here there is a wall, and here there is a window, glass window. So this column is designed for the full height. Remember, full height. But now the height will become half, right? So again the column becomes short. This is again a case of short column, right? So what happened in case of short column? This is very important. We have to understand that the stiffness is 12 EI upon L cube, right? 12 EI upon L cube. When we're talking about the stiffness, Suppose if I'm taking, it is 12 EI upon L cube. Right. Now just imagine this height will become L by 2. What will happen? If this height L will become L by 2, the L by 2 means L by 2 cube. It will become, stiffness will become 8 times high. 8 times. It means your building is going to attract 8 times more force. This column is going to attract 8 times more force. This column, suppose able to resist 100 kilonewton force, right? Now it is going to attract 800 kilonewton, right? So higher earthquake force is attracted by this column because its stiffness increased, right? And that is the problem, and that therefore the short column is not good for the earthquake. Short column is good for the axial loading, but is not good for the lateral loading. So as it will become short, it will attract higher earthquake force, and it will observe the damage because it goes beyond its capacity, right? So what is the solution? The solution is very simple. You provide a gap here, because we have designed this column for the full height. Remember, this for the full height we have designed, right? So you have to design, you have to allow this column to move by full height, right? Then it is okay, then your design is okay. So only thing is that you have to go for the separation gap, right? Separation gap you have to provide. The another problem is the torsion. When your structure is unsymmetrical, your building, for example, this is the case. You have a column on the front side and you have a RCC wall on the back side. Now what is happening? This will become too stiff, right? This will become too stiff, and this portion, this is very flexible. So when the lateral load will come, this flexible portion will move more and this stiff portion will move less. So you have a torsion in the building, torsion in the column, right? And you can see the damage in the building. You can see this is a failure because of the torsion, right? Then we have two buildings which are very close to each other, then they will hit each other, right? So what is happening here? If the gap between these two is not sufficient, then this slab may hit this column, right? Now we have designed this building properly, right, for earthquake and everything, but during the earthquake this slab is hitting the column and we have not designed for this impact. And what happened? This column may collapse, right, and may your structure collapse, right? Look at this damage, right? This is happening. Look at this, right? Because of the pounding, the building collapsed. Look at this. Look at this. This is collapsed because of the pounding. So when the two buildings are very close to each other, you have to design the gap, right? You have to design this gap in such a way that if both the buildings are moving towards each other, and even though you must have sufficient gap between them, right? If it is not there, then a pounding is going to take place, right? So how you design? The design is very simple, that you have to design the gap. So you have to calculate the deformation of the building 1. You have to calculate the deformation of the building 2, and you have to add and multiply by the response reduction factor. That is the gap you have to design, right? Building with the setbacks. When the building with the setbacks, these buildings are generally not performing well. The reason is, you see, this is the particular point where stiffness changes. You have many more columns here, and then these columns are reduced here. So there is a difference in the stiffness of these two, the lower part and the upper part of the building. Same way here. Here you have many columns on here, and then it is reduced at this particular level. So there is a difference. So these are not performing well. So what can we do is we go for the separation gap, right? We go for the separation gap. Right? Separation gap is the solution, and we try to make it symmetrical, right? And then we have a lift. Uh, Generally, the lift is made up is a connection of the lift well with the main structure, right? Generally, this lift well is made up of RCC, right? When it is made up of RCC, it behaves as a shear wall during the earthquake, and if it is not properly connected with the main structure, then this is going to happen. Your main structure collapse and your lift well remain as it is. So improper connection between the lift well and the main structure is another case. So you need a strong beam for the connection, so that during the earthquake, the load of your main structure is transferred to this shear wall of the lift well, and your lift well may help your main structure to survive, right? And improper connection of the overhead water tank with the main structure. This is the overhead water tank, right? How we design? We find out 4 columns, and then we are placing the water tank on it. Right? So for dead load and live load, it is okay, right? But for the lateral load, it is not designed, is not proper, because during the lateral load, the force is acting in the horizontal direction, and your water tank is collapsing like this, right? This is happening. You can see the improper connection. Generally, this cantilever projections or these columns, generally we are designing for the 5-time acceleration, right? This is very important, 5-time acceleration, and the liquefaction potential, right? So when we are knowing that my structure is located on a cohesion less soil and the water table is high, you have to be very careful, right? And you have to assess the liquefaction potential, and you have to take the actions to avoid the liquefaction, right? So here you can see the liquefaction taking place. Nothing has happened to this building, right? Because of the liquefaction, just you look at the whole building is almost safe. Nothing has happened, but it is tilted because it is on a liquefiable soil. Look at this is the tank, which is tilted by almost 21 degree during the Bhuj earthquake, and again it was restored, but this is because of the liquefaction. So you have to eliminate the liquefaction potential of the soil, right? So what are the factors for the good seismic performance? The first is the configuration, architecture configuration, then structural design. We have to talk about, as a structural engineer, we have to talk about the adequate lateral strength, stiffness, ductility, and integral action. These are the 4 important parameters structural engineer has to look at. We have to also design the non-structural member, and we have to look at the quality of construction on site, right? These are the things you have to observe for the good seismic performance. So very simple thing is the implementation of the code, but it is always a challenge, right? When the provisions of the people are, or the civil engineers are excusing that it is very difficult to execute the codal provisions given in Indian code on site, right? But one simple statement is that for the safety in future earthquakes, all the provision of the code should be followed in design and construction. This should be made mandatory in building bylaws. That's all. This will make a lot, or this will solve a lot of problem, I tell you, right? Then what is another challenge? The another challenge is the content of the code is the another challenge. The IS 875 part 1 to 5, right? Now the IS 875 is for the loading, right? The 1, 2, 3, 4, 5. The this 1 to 4, they are dealing with the dead load, superimposed load, wind load, and snow load. And the 5th part is load combination. Seismic load is not included in 875. Remember, this seismic load, it must be a part of IS 875, right? Why it is treated separately? IS 1893 is published for this, right? IS 1893 is published separately. It should be a part of 875. Most of the code, foreign codes, the earthquake is considered as a part of uh, the code which are related with the loads, right? But in India, the seismic loads are treated separately. So that is the problem. So sometimes after 2001, many structural engineers are not knowing the 1893 is there, right? So that is the problem. The another thing is the revision of the code. 1893 is first published in 1962. Then after 4 years it is revised. Then again 4 years revised. Then again 4-5 years. Now after 75, after it revised by 10 years, then it was revised by after 20 years, right? Now if you look at the geometric progression, it revised up into 2040. But we are lucky that again we have a good revision in 2016. After 2006 to after 14 years we have another revision we have, and we have okay. So the important thing is if you look at the 1984 code, there was a 1984 code, right? And there was an earthquake in Latur, right? And then the revision of 1984 code was started, right? 1984 code was started after 1993, right? I am talking about 1893. Remember, I am talking about 1893. And this revision is completed in 2002. Remember, after 2001 Bhuj earthquake. It means we need one earthquake to start the revision. We need another earthquake to finish the revision. Now, the problem is definitely with us because we are not contributing in this process of making the code. Right, our contribution is required. I think few dedicated persons are contributing to in this making the code. Right, so all of us have to participate in this code. So part 1 to, if we're talking about the IS 1893, part 1 to 5, 1 to 4 published, but still part 5. There are 5 parts, but only 4 published. 5th is still remaining. Right. We have IS 4326 published in 1967 and revised in 1976. Right. Now, if we talk about the IS 13920, it is a code of ductile detailing published in 1993, and after 1993 we have a code in 2016, right? So almost after 23 years we have a ductile design and detailing, right? So many years. So the revision of regularity of development of the code is required for the better construction. The improvement in the research is required, right? You see, India is divided into 4 seismic zones: zone 2, 3, 4, 5. And if you look at this, Gujarat is in zone 3, majority portion, almost 98%. 98% Gujarat is in zone 3, 4, and 5. So Gujarat is having high seismic risk. At the same time, you look at north and northeast boundary, they have the highest seismic risk, right? Zone 4 and 5, right? But you see, the improvement in the research is required. In 1993, there was an earthquake in Latur. Right? At that moment, the Latur is in zone 1, and after earthquake, the Latur was put in zone 4 after earthquake. Right? So this should not happen. The zonation should be based on scientific research, right? But still, we need a good research in this area. ISR, Institute of Seismological Research, is doing good job, but it is limited. Still, the micro zonation of the whole country is required. Instead of that, some pockets have been done right now. Then, what are the initiatives in Gujarat? Some good initiatives have been taken after 2001 earthquake. The earthquake engineering is included in the curriculum of civil engineering and architect in 2003, and it was made elective in 2016, right? So this is what we try to forget the earthquake, right? So we made earthquake engineering as an elective, and right now hardly 10% students or less than 10% students are opting for this particular subject, because the other subjects look very easy as compared to this subject, and therefore uh, it hampers the capacity building process in Gujarat. We have taken a good initiative in 2003, but again everything is gone in 2016, and right now we are moving again the same thing what happened before 2001. Right, we have to go for the capacity building initiatives. Right, the training of the engineering teachers were taken place, training of the engineers and architects taken place, professional practicing engineers, government departments, mission training, and everything is taken place after 2001 Gujarat earthquake. Very two organizations which came up, GSDMA is came up, and the ISR, Institute of Seismological Research. GSDMA is talking about the seismic code awareness and about the building disaster management policy. ISR is talking about the seismic microgeneration, research in seismology, monitoring. But you see, for the earthquake resistant design, we need a technical institute, right? But no technical institute came up after 2001 to dealing with the safety issue in the structures, right? So the most of the resources are diverted toward the seismological research and the instrumentation, not for the addressing the problem of unsafe construction. No, we have not done it. The enforcement of the framework for the code compliance, that is required, right? So right now we are, if you see, if the design is submitted, the authority is only checking the architectural part. The structural design, nobody checks in the authority. Third party checking and nothing is there, right? So if you design, the corporation or the urban development authority accepting your design, considering the signature of the structural designer, right? So I think we have to address this part. Then this is very important thing which is done. Gujarat Council of Professional Civil Engineers, right? This came in picture in 2006, right? You see, right now what is happening? Right now, if I want to go for the structural design, what is the process? It is based on the experience, right? I did my Bachelor of Engineering. I cannot design, right? But then I go for the I'm having the site experience of 5 years, and after that I can design, right? So it should not be based on the uh, year of experience, right? But it should be knowledge based, right? That is to be required. So licensing of structural engineers are required. It should be based on competence, right? So in the foreign countries, they conduct the regular examination. To take the structural engineering license is a tough job, while here it is the easiest job you have, right? So right now, when this council came in picture, they start taking the exam of structural engineers and the general civil engineer. So the Gujarat Council for Professional Civil Engineer came in picture in 2006, and after 16 years it became active. Remember, after 16 years it became active. The requirement is required for peer review of important projects. Now this is going on. I think this is good progress is made. Structural documentation is needed, and the sample checking of drawing and construction on site, just like income tax return is required, right? Now I think you need energy, so I put the slide of Parle-G, right? So you need some glucose. No, you see, what I want to mention here is, when you are purchase uh, a Parle glucose biscuit, and if you uh, if you see the instruction which is on the wrapper, everything is described what is there in the biscuit, right? It is worth only 2 rupees, and you get each and every information. But when you purchase your house, what you get? You get nothing. You get document. You get आपका दस्तावेज आपको मिलेगा. And what you see the aesthetic part only. You never look at the structural safety part, right? When you purchase a home, So you have to look at the structural safety when you purchase, but nobody is going to give you the structural design. Nobody is going to give you structural drawings. They only give you the plan, and they will give you only the document, the service you want, right? So that is the main problem. If I am purchasing my house worth 2 crore rupees, and I must know what is there in my column, what is there in my beam, as far as my house is concerned, right? But nobody is giving us. So that is again a problem. If they are they are giving us the actual structural design, then before giving us, definitely they will check, because it can be challenged in the court, right? But right now this practice is not there in India, and that is the problem, right? So there is a legal clarity on the code enforcement is required. You need a certification of the mason is also required. So uh, uh, the Gujarat Council for Professional Civil Engineer Act is there, and right now work is going on. So if you look at this, the India is observed great earthquakes, and regular occurrence of the earthquake is also a challenge. Remember, occurrence of the major earthquakes. We have an earthquake in 1988. We have Nepal, 91 Uttarkashi, 93 Latur, then 7 Jabalpur, 1 Bhuj, 5 Kashmir, 11 Sikkim, 15 Nepal, and then again 21 Sikkim, right? So most of 2, 3, 4 years, the earthquake are coming. They are not great earthquake, but the frequency of earthquake is increased after 1988. And you see, after 1950, we don't have seen any great earthquake, right? So if you look at this, we have 4 great earthquakes, right? 4 great earthquakes: 1897, 1905, 1934, 1950. So 1897 to 1950, in 53 years, 4 great earthquakes we have. 4 great earthquakes we have. It means, what is the return period? 13 years. Every 13 years, India had observed a great earthquake. But after 1950, it is almost 72 years. 72 years, and there is no great earthquake in India, right? What is the meaning? The meaning is, there is a very high probability of having big earthquake in the northern part. There is a theory of seismic gaps. If you look at this red, the red will show you the past significant earthquakes, and the blue will tell you a possible seismic gap. It means these are the red means the earthquake already taken place, and the blue part is showing that no earthquake taken place. Means you see, these are the region where next earthquake may come. Right, in the blue region, next earthquake may come. You have to observe. So theory of seismic gap is saying that lot of energy is stored there, and these are the regions of having a big earthquake, right? Now question is arise, we have a lot of problem, but is there any success story from India? The answer is yes. Long time back, in 1930, in Balochistan, we have a good example. 1897 Assam, we have 19th century Srinagar, we have a good example. We can see this. This is a Rajivari Construction in Srinagar, right? They are constructing the masonry house, and then they are putting this wooden bracing, right? We are putting steel bracing. Now they are putting wooden bracing. You see, they haven't learned any earthquake engineering, but from their experience, they have learned, and they have put this bracing in 19th century in Srinagar, and this building performed excellent during the earthquake, because these bracing are very ductile in nature, and they absorb lot of energy, and they provide they increase the stiffness and also the ductility, both the things. In 1897 Assam earthquake, it was 8.7, right? And almost the mean radius of perception is 900 miles. Remember, and the serious damage in 300 miles is almost 480 kilometers in a radius. That was and at that moment, upthrow of the object. Upthrow means the stones are moving in the upward direction. It means the vertical acceleration is more than 1 g. That was observed for the first time. And because of this earthquake, the Mercalli scale was revised and modified. Mercalli scale came in picture, right? And the intensity scale 12 comes in picture because of this Assam. And what they have done, they have developed the ICRA housing. ICRA housing. What ICRA housing is, I think picture is not there. In ICRA housing, what they construct their houses with the stone up to the plinth, and then above plinth they are constructing with the wooden houses, right? And they are knowing the wood perform better because it is very lightweight and also the ductile. So these two things they were included. They learned from the past. This is very important. What happened in Balochistan in 1931? There was an earthquake of 7.4 in Balochistan, and lot of damage had been observed, and 100% died. And the railway was worried about it, and so what they did, they appoint S.L. Kumar, only who is young, 28-year-old. He designed earthquake-resistant quarters for the railways. So railway appointed S.L. Kumar. They said that you design our building such a way that it resists the earthquake. And this S.L. Kumar took the challenge. And in 1933, he presented a paper. He talking about the earthquake-resistant construction. He talked about the design and cost implication. He has given the first seismic zone map of India, and he has given a seismic coefficient for the two types of building, right? So in 1933, he had given this, right, from his own study, right? So this is the early zone map given by the Kumar, right? And there was an earthquake in 1935, Quetta earthquake. It was 7.6, 30,000 people died, right? 40% population was gone. And the buildings which were designed by the Kumar, S.L. Kumar, nothing was no buildings were collapsed, and excellent performance was observed of this building, railway quarters, which were designed by the S.L. Kumar, right? So at that moment, earthquake engineering was not there, but Kumar has designed these structures on its own, and he has done a remarkable job, right? And what he did, he has designed. He was knowing that masonry is performing very poor, so he has designed a new bond, is known as a Quetta bond, in which you can pass on the reinforcement, and this reinforcement will take the tension created during the earthquake, and your structures were not collapsed and performed really well in that, right? So a fantastic work is done from 1897 to 1935, but it was led by the professionals, remember, not by the academician, right? Not by the academician. And if you look at, right now we are more vulnerable as compared to earlier. So the one option is confined masonry. So confined masonry is a new addition which is made in 2022. The code of confined masonry is published, and it is a good addition. So now I'm going for my concluding remarks. A mega earthquake disaster awaits India, particularly in the northeast boundary, right? So, and we are knowing that most of the constructions are deficient. So you have to understand the solution lies in the building, not in the earthquake, right? If the big earthquake will come, definitely we are facing a big problem. If earthquake in India is taken place in Bhuj, almost 13,805 people died, and the same earthquake taken place in America, only 50 deaths had been observed, right? But if it is taken place in a developing country like Iran or Turkey or Pakistan, I think thousands of deaths will be observed. So earthquake safety is a long and hard struggle. No instant result we are going to get, right? Why I'm saying this? Because the California has started earthquake safety program 70 years back. I tell you, 70 years back means 1950 they started. They started the retrofitting, seismic retrofitting of the bridges in 1971, and still continues, right? So America started the program in way back 70 years back, and still it continues, and we haven't started. So how much time we need, that we have to decide, right? So the last few points I want to mention is the seismic design is a shared architectural and engineering responsibility, right? In resistance to gravity, अब ग्रेविटी का डिजाइन करते हैं, और तो हम आर्किटेक्ट और स्ट्रक्चर इंजीनियर अलग अलग डिसीजन रहते हैं, तो ठीक है, लेकिन when we are talking about earthquake, engineer and architect have to work together. If they work separately, it's a formula of disaster, right? So architect and engineer has to work together, right? And who can make them work together? Building owner, right? He can work them together, right? So good interaction is required between architect and the engineer is required. Then and then we have a good configuration and good structural system, right? So engineers and architect has to work together, but this is the scenario right now in India. They work separately, and this is going to happen as a part of the teamwork, right? So the cost of earthquake resistance is not that great. It is almost the 8% of the normal estimated cost, and we have to go for it. So this cost of the earthquake resistance depends on the planning approach and the applied method. So no significant additional cost. How much we have learned? So this is the table I want to show you. हमने क्या क्या सीखा है. कोई भी बड़ा earthquake आता है तो क्या क्या हमारा रिस्पॉन्स क्या होता है, हमारा रिएक्शन क्या होता है. पॉजिटिव और नेगेटिव दो चीज होती है, राइट? सो अर्थक्वेक आया, 1 मिनट के अंदर कोई पॉजिटिव नहीं होता है. वी आर वेरी पैनिक. 1 मिनट टू 1 वीक का टाइम फ्रेम हम ले ले तो आफ्टर शॉक आते हैं. नाउ व्हाट इज द पॉजिटिव थिंग? रेस्क्यू एंड सर्वाइवल स्टार्टेड, बट अभी भी हमें डर है कि अभी कुछ ऐसा ना हो दूसरा बिल्डिंग गिर जाए. 1 वीक टू 1 मंथ आफ्टर शॉक कम होते हैं. शॉर्ट टर्म रिपेयर स्टार्टेड, लेकिन अब लोग ब्लेम करने लगते हैं बिल्डर्स को, डिजाइनर्स को, ऑफिशियल्स को. 1 month to 1 year लॉन्ग टर्म रिपेयर्स वो चालू हो जाते हैं. एक्शंस फॉर द हाई स्टैंडर्ड्स, हम काफी कुछ चेंज करना चाहते हैं. देन 1 year to 10 years हमारा इंटरेस्ट कम होता है, एंड देन 10 years to नेक्स्ट. अभी जो हम स्टेज में है गुजरात में, ये यही है, रिलक्टेंस टू मीट द कॉस्ट ऑफ सेismic प्रोविजंस, इंक्रीजिंग द नॉन कॉम्प्लायंस विद द रेगुलेशन, राइट? अभी उसके बाद और अर्थक्वेक आएगा और फिर से यही स्टेप हम रिपीट करेंगे, राइट? सो दिस इज व्हाट वी हैव लर्न, एंड दिस इज द photograph I want to show you. We are like a Ghazni. We have a memory loss, right? We forget earthquake very fast, and that results into the unsafe earthquake society, right? So pay a little now or lot later, we have to contribute, right? So what can we do? We cannot predict earthquake or stop earthquake event to happen, but we can prevent collapse of the structures by adopting good technology and good practice, right? This is in our hand, and who can do that? It is engineers and authority, right? It is our responsibility. Time is started, so we have to start, and we have to climb this ladder. We have to take many steps to make the society earthquake safe, right? So let us prepare ourselves to reduce earthquake to a nuisance rather than danger. Convert earthquake disaster into a routine event, right? So thank you very much for your patience hearing. Thank you very much. If you have any questions, you can ask, please. Yes, please. If you have any questions, you can ask.
Participants, you may unmute.
Yes.
Kamini madam, go ahead.
Yes, ma'am.
Yes, Sanghvi sir.
Yes, yes. Please.
Sir, very informative lectures. Thank you for that. Sir, I have one question regarding short column.
Yes.
If it is not possible to avoid short column, means
Yes.
design, then is there any measures to avoid the failure of that column? Because in hilly area, sometimes it is not
Very
possible to avoid short column.
Yes. Very simple thing is that if you don't avoid it, then you have to design it. That's all. The problem here is
Okay.
we are not able to identify the short column problem. We are not able to identify. We have constructed a wall, right? But we haven't identified the column become short, right? Because we have done nothing wrong, but the principally it become wrong, and that is the problem. And therefore, if you are not able to avoid it, then you have to design it for that much force, and then you can avoid these columns, right? This mistake is made totally unintentionally, I tell you. The pictures which of the short column failures, in nobody have committed intentional mistake, right? It was not intentional mistake, it was unintentional. They have constructed and they don't realize that this become a short and it is going to attract a larger force. That is the problem.
And
Yes.
sir, one more question is that for liquefaction, is there any test that we can do to test whether it is possible during the earthquake liquefaction?
No. Basically, we have to go for the geotechnical investigation, and we have to look at the profile of the soil, and if it is a cohesion-less soil we have, and then we have to understand that if cohesion-less soil is there and water table is high, then we have to go for the measures to avoid the liquefaction, like stone columns we are providing, we are compacting that soil properly. So we have to take all these measures so that the pore pressure cannot build up, and the pore pressure will release and nothing will happen, right? What happened in liquefaction, you see, the soil is getting strained from two perspectives. One is cohesion and second is friction, right? Now, when I'm talking about the cohesion-less soil, there is no cohesion. So the strength of cohesion-less soil is depend on only friction, right? Now, when the water table is high and during the earthquake, then water enters into the cohesion-less soil, then the friction will become zero. So now, in cohesion-less soil, there is no cohesion, no friction. So it behaves like a liquid, right? So what is necessary thing? The necessary thing is that you have to create a condition such that no pore pressure should develop, right? And the shear strength of the soil should remain as it is, right? So that thing, like you provide the stone column and you allow the water to escape from that, or you compact the sand before the construction, that can be done, right? So there are numbers of options we have to avoid the liquefaction.
Thank you, sir.
Yeah, perfect. Any more question, please?
Please.
Yes, thank you. Am I audible?
Yes, Dr. Mohit, you are audible.
Thank you, sir. Very informative presentation, and it is quite heartening to know that you have presented a full picture of what may come in the coming years. So we are due for a big earthquake. The earthquake will take place in Indo-Gangetic Plain. We have also identified the potential pockets. Now, so far as the measures are concerned, I don't see that kind of urgency in any government project to save people, because Indo-Gangetic Plain hosts maybe, I don't know, 2-3 billion people or something like that. Majority of population in North India resides in this region. So the casualty will be very high. And second thing is the microzonation exercise that you said should be done. I don't see, we did a project in Gangtok and Shillong where we attempted this kind of exercise of microzonation at the ward level. But apart from that, I didn't find any other measures taken by the government or any other agency in our country. So can you put some light on this?
Yeah. Basically, as far as micro donation is concerned, uh, we have not done the micro donation of the whole India. I tell you. I told you that in Latur, earlier it was in zone 1, and then directly after earthquake we put Latur in zone 4, right?
Right.
So this is what we are doing. But you see, right now, if I'm talking about the Gujarat, in Gujarat we have Institute of Seismological Research, and they have done the microgenation of the Kutch region. Then they have done microgenation of Dholera, that is the SIR special investment region. Then
Right.
microgenation of Ahmedabad and Gandhinagar, it is done by the ISR, right? But
Right.
it is basically right now it is not the mandate of the microgenation of the whole Gujarat, right? So that is the main problem. And at India level, we have a microgenation of the Delhi, we have a microgenation of the Chandigarh, and we have certain other pockets in which microgenation had been carried out. But again, it is not this mandate is not given by the government. So right now it is not in the priority. That is the problem. So right now our problems are something different as compared to like we have major other problems we have. So the India is addressing those problems rather than the problems related with the earthquake. So that is
Yes, very right. Because what I feel that our approach is more reactive than proactive. So we are waiting
Yes.
for that to happen, and then only we will wake up, which is a wrong approach.
You see, I had given you example. In 2003, the earthquake engineering was introduced in the curriculum in the Gujarat, and then 2016, even university tried to forget the earthquake. They said that okay, now if it will be the elective, there is no problem. So you see, a lot of awareness had been created from 2003 to 2016. But after that, again, we start forgetting the earthquake, and I think we will see the result in the next earthquake. That is the main point, right? So we have to be little serious, and we have, you see, we need a political will. Once we had a political will, we can do wonders in this area also.
Right, agreed.
Yeah.
Thank you, sir.
Anyone else, please?
Audience, questions? Further questions? Participants? Okay. I guess not, sir. It has been a very rigorous and very informative session for all of us on this interesting site details of starting from scratch, what earthquake does, how to remedy file, and what can be our future strategy for this so hand over now to Roshi and this session. Next session we will be starting. So Roshi, please.
So before that, just I want to thank my guru, Dr. S.K. Jain, Dr. Murthy, and Dr. Rai, before I conclude my session. So thank you to all these professors who have contributed a lot in understanding the quick restrict concepts. Right? So now, Rishit, you can go ahead. Thank you.
Thank you, sir. It was such an informative session. Each aspect encompassed in a detailed manner and portrayed with some astounding pictures and slides. This would have surely benefited all the participants in enhancing their knowledge. Lastly, on behalf of the Applied Mechanics Department, I would like to thank you, sir, for sparing and sharing your valuable time and outstanding knowledge with us. Now, please, every participant, take a note. We will have a break till 1:30 p.m. The next session will be conducted by Dr. P.K. Garg, sir, on role of drone and geoinformatics in disaster risk resilience and resource mapping at 1:30. So you all can leave this meeting and join at sharp 1:30 p.m. Thank you. And validatory function will be on continuous with this session.